Besides these small games and toy examples, search problems occur in many real-world applications in which we need to devise some search algorithms in order to find some solutions to problems. These problems include routes finding problem, in which typically this is our map search problem, where we need to go from a location to another one using links or transitions on a map. Examples of applications include tools for driving directions in websites, in car systems, etc. A second popular application of search algorithms is traveling salesperson problem, in which the goal is to find the shortest path or the shortest tour to visit each city exactly once. So you have someone who is a salesperson and he doesn't want to go through cities several times. So the goal is to find such a shortest path. This is the goal of the search. So it's known as an NP-hard problem in computer science, and there have been a lot of efforts and research in finding a smart algorithm to find such a short path. But this is typically a search problem in artificial intelligence. A third very successful application of search problems is VLSI layout. That's actually a very technical aspect in which we need to position millions of components and connections on a chip to minimize the area, shorten the delays, etc. The aim is then to put a circuit components on a chip so as they don't overlap and so as you leave some space to the wiring and the connections. This is typically a very complex problem, and the goal is to optimize the area and optimize the position of the components with respect to each other. Robot navigation is another special case of route finding for robots with no specific routes or connections. So you don't have a map to rely on to go from point A to B. Rather, we have a continuous space in 2D or 3D in which the robot needs to navigate and move around. So the state space and action space here are potentially infinite, and you need to optimize the search through this space to find the best, to find the path to the goal that we want to achieve, which is moving the robot from one point to another one. Another successful applications of search problems is the automatic assembly sequencing, in which the goal is to find an order in which to assemble parts of an object, which is generally a difficult problem because you can't undo it. If you undo it, you need to disassemble what you have done so far. So it's an extensive and expensive geometric search of the different possible sequence of actions for which you need to make the assembly of the object parts. A last successful applications of search in AI is protein design, in which the goal is to find a sequence of amino acids that will fold into a 3D protein with the right properties to cure some diseases. So this is a typical application in which we are going to search for possibilities to find sequence of amino acids. So I give you here just few examples of applications to cite just some of them, but the potential applications of search algorithms in AI is quite large. So now that we have seen some typical examples of AI, some toy examples and also real-world examples, let's dive into the more technical aspect of search problems in AI and see how this is achieved, let's say for route finding on the map. So first of all, it's important to distinguish between what we call a state space and a search space. The state space is typically the physical configuration. This is really the different states in which your problem is evolving. So for the example of the 8th queen, for example, you have the state space would be the set of all possible boards on which you have the numbers moved somehow. So for example, you could start with 1, 2, 0, 3, 4, 5, 7, 1, 2, 3, 4, 5, 6. This could be one possibility. Another one could be where the 1 is here, the 2 is here, the 3, etc. So all possible configurations of your problem constitute the physical configuration and constitute the state space of the problem. In contrast, a search space is an abstract configuration of the problem, which actually is represented by what we call a search tree or graph. Right? So this is actually modeling the possible solutions to the problem. The search space is typically represented by a search tree that actually models the sequence of actions. A search tree would look like something like the root that represents actually the initial state. From the initial state, you have branches that actually lead you to other nodes that could also lead to other nodes. Okay? So the branches represent the actions that we could do. These are the actions. For example, drive from city A to city B, or just slide the tile on the 8 puzzle, if you know. So the branches typically are the action that you can do to move from some state to another one. Okay, so we have nodes. Each node has typically a parent. It has children. It has some depth, right? It also has a state in the state space. So remember, the state space is the physical configuration. So if you are moving a tile on the 8 puzzle, here you have configurations of the tiles, and here you have, when you do these actions, for example, sliding the one from left to right, will bring you to another configuration. So a node typically has this important information, which is parent, children, depth, path cost, and the associated state in the state space. So keep this in mind when you design your search problem. Finally, we will define the function that's called expand, that, given a node, creates all the children for those nodes. This is what defines actually the problem formulation of the state and the search space. More specifically, the search space, often represented by a search tree, is divided into 3 regions. The explored region is actually also called the closed list, or the visited set, is all the nodes that are already visited in the search tree. The frontier is actually also called the fringe, or the open list, is what is about to be explored. That's getting ready in a line, or in what we call the frontier, and ready to be explored next. And finally, we call unexplored nodes those that are remaining yet to be explored in the search space. So the essence of the search is moving from the nodes from regions 3 to 2 to 1. So this is really going this way. So we start with everything in the search space that is unexplored, and we're going to move them as depending on the search strategy that we adopt, move them into the fringe and then move them into the state of being explored. So this is really an important piece of information when you develop and you implement the algorithms for search, which is, if you want to you have a full tree that you are going to explore, but then you will have to decide how to explore them. So they're all set and explored, and then you're going to move them depending on your search strategy, which is the order of your moves into the frontier and then to the stage of being explored. In the following, we adopt some color coding to show on the search tree when we explore the search space. So I'm going to show with the orange nodes all the explored nodes. The elements on the frontier, or the nodes on the frontier, will be coded as in gray. And finally, the unexplored node will be left white. Black will be used to represent the failures on a node in which there is a failure on the search space.